Welcome to Course 101, TiDB Technical Essentials. This is Module 2, TiDB Server. My name is Jeff and I'm your instructor for this module. When you complete this module, you will be able to describe the TiDB Server architecture, describe the role of TiDB Server, describe the TiDB Server process, and describe the TiDB Server cache. In this module, we will begin with the internal thread pool and cache of TiDB Server and introduce the key functions and hierarchy of the TiDB Server. First, let's get to know the core thread pool and cache of TiDB Server. Let's take a look at the main functions of TiDB Server. So let's summarize the core functions of TiDB Server one more time. TiDB Server is responsible for the following. 1. Handling client connections. Users are authenticated by username and password. Database privileges are primarily enforced by the protocol layer. 2. Parsing and compiling SQL statements. The TiDB server parses and compiles SQL statements. During the compilation process, it optimizes and generates a distributed execution plan. These tasks are performed by the parse and compile modules. 3. Converting relational data to key value pairs. Since data is stored on TiKV in the form of key value pairs, there's a big difference between relational data, such as table, index, row, and a key value structure. In order to execute SQL, TiDB must convert relational data to key value pairs so that it can be stored in TiKV. 4. SQL statements execution. Using the compiled execution plan, SQL statements are executed on TiKV in batches. The data is read by the executor module, the KV module, and the DISSQL module, and the transaction-related operations are completed by the transaction module and the KV module, KV meaning key value module. 5. Online DDL execution. Data definition language, DDL, operations do not lock tables. The work is performed by the schema load module, worker module, and the start job module. 6. Garbage collection. The garbage collection background module is responsible for recovering old versions of data that have expired. We will cover this in detail in the TiKV module. And finally, cached table. Remember, this is a new feature in TiDB 6.0. This function is suitable for hotspot subtables that are frequently accessed and rarely modified. That is, the data of the entire table is loaded into TiDB server memory. Since the query doesn't have to read from TiKV, it is significantly faster than having to go to disk. Parsing and compiling are important functions in TiDB Server. Let's introduce them separately. First, the parse module. Parse uses Elixir, in this case Lex, to parse SQL statements into tokens, one by one. Next, it uses Yak, yet another compiler, to generate a tree structure that is an abstract syntax tree. This is usually referred to as AST. It can then be identified and compiled as shown in the diagram. Next, let's look at parse and compiling SQL statements. This is the compile phase. After the SQL statement is parsed, the AST syntax tree is generated and passed to the compile module. The compile module performs the following tasks. First, it performs validation on the query and checks the legality and name bindings. Next is logic optimization. This process makes logical transformations based on the equivalent exchange rules of relational algebra. It consists of a series of optimization rules. The logical optimization rules of TiDB include column pruning, maximum and minimum elimination, projection elimination, predicate pushdown, subquery decorrelation, outer join elimination, aggregation elimination, and more. Once logical optimization completes, physical optimization begins. Based on logical optimization results, physical optimization considers the distribution of data and decides how to select physical operators. Part of the physical operation process involves selecting the optimal execution path. This process depends on catalog statistics. The more accurate the statistics, the better the execution plan. TiDB optimizes queries using techniques such as data read method, join method, table connection order, and ordering. Finally, TiDB Server creates an implementation plan. It's worth noting that physical optimization requires querying the metadata of the tables that participate in the query. Metadata is used for legality checking and statistics. The metadata and statistics of the table are stored in the TiDB Server cache. Another very important job the TiDB Server performs is the conversion of relational data to key-value pairs. Remember, TiDB Server works with relational data, and TiKV works with key-value pairs. Let's use an animation to explain the mutual transformation of relational data to key-value pairs. The diagram shows a relational table with a numeric column as the primary key. We mean number. The remaining columns, name, birthday, cell phone, and score, make up the value part. The new column, along with the ... signify the separation of key and value. Unfortunately, our primary key can only uniquely identify a single row in a single table. Our database will have many tables. We need a way to identify a single row in a specific table. So, let's add a column that will uniquely identify a table. Our new column is table no, which really means table number, and that will handle this. When we combine table no and no, think of it as row ID. Using this approach, the row of data has a database level global key. I know what you're thinking. What about tables that don't have a primary key? Well, TiDB adds a hidden column, row ID, to all relational tables. If the table has an integer primary key, then the value of the primary key will be used as the row ID. Otherwise, the generated row ID will act as the primary key. Where table ID is unique in the whole cluster, index ID row ID is unique in the table, and these IDs are of type integer 64. Now that we have relational data in key value format, the following question arises. How are these key values organized? Our diagram shows us that combining a table ID with a row ID allows us to uniquely identify the rows in our table. We don't show it here, but imagine that there are multiple tables stored in the TiKV key value pair structure. The combination of table ID and row ID will enable TiDB to find any specific row. We call a set of key values in the database a region. A region is also the logical unit in which we read data. We will see on the next diagram that the data in a region is replicated. Obviously, storing all of our data in a single region doesn't make a lot of sense. As a result, when a region reaches a certain size limit, it splits. By default, one region in TiDB is 96 megabytes maximum. That is, when 96 megabytes is reached, the region will be split into two regions. This avoids the problem that the region is too long. It can also prevent a region from becoming hot. Hot regions have lots of activity. This can cause performance problems because the activity isn't spread across TiKV nodes. The data in a region is replicated. By default, there are 3 replicas, and the replicas are distributed to multiple TiKV storage nodes. This ensures that our data is naturally dispersed and distributed. And like we said, spreading our table's data across multiple TiKV nodes increases parallelism and therefore performance of our TiDB database. The region distribution information is stored in the PD, and each time the SQL statement is executed, the location of the region where the data can be found is read from the PD. Our diagram shows that the data stored in the region is replicated across multiple TiKV nodes. The diagram skips the replicas too. Think of each region as really a replica of a single region's data. We will cover this in detail in a later module. The thread pool modules related to SQL read and write are shown on this diagram. We will introduce the SQL reads and writes process here, but we will cover them in detail in Module 5, TiDB Database SQL Execution Flow. So let's take a look at the relevant modules. The executor module is shown towards the top middle portion of the diagram. Execution begins according to the tree execution plan generated by compile, and each layer calls the methods of the next layer to obtain results. Next, the dist SQL module is below the executor. In order to avoid complex logic coupling with the SQL layer, TiDB extracts a unified distributed query layer interface, the dist SQL module. The dist SQL module is a layer of abstraction between TiDB Server and the coprocessor. The coprocessor can handle aggregation, filtering, and other tasks. Since it lives in the TiKV component, it increases performance by minimizing the volume of data being passed between it and the TiDB server. Dist SQL encapsulates the lower coprocessor request and provides a simple select method for the upper layer. It performs a single table calculation task. The top-level SQL statement may be complex operators such as join and subquery, involving many tables, while dist SQL only involves data from a single table. A dist SQL request involves multiple regions, and we want to execute a coprocessor request once for each region involved. Next, the TiKV client module is shown below dist SQL. The TiKV client module, and in this case it's going to be TiDB Server, but it doesn't have to be, is primarily responsible for sending read and write requests to the TiKV module. The first type is raw KV request, which is a simple request to obtain a single row of data, such as an equivalent query based on a primary index or a unique index. The second type is coprocessor request, which requires that the computation also be pushed down to TiKV's coprocessor framework, as we said before, things like filtering, aggregation, or column projection, and other things. Next, the transaction module is shown towards the top left side of our diagram. As its name implies, the transaction module handles transactions. This includes two-stage commit, pessimistic lock, optimistic lock, management, etc. Next, we have the KV module. It's towards the middle left of our diagram. The KV module handles transaction-related requests to KV. For example, KV get and batch get. Finally, we have the PD client module. You can find it in the upper right-hand side of the TiDB server. It is a module in the TiDB server that handles communication with the PD cluster. TiDB database supports online data definition language commands. To save time, we call this DDL. Online DDL means that DDL operations such as create table, create indexes, do not lock tables, and data manipulation language statements, or DML, are not blocked. Let's take a look at the various modules required to execute DDL. First, the entire TiDB database only allows one TiDB server to perform DDL operations at a time. In order for a TiDB server to execute DDL, it must be assigned the owner role. Although every TiDB server has a worker module that can handle DDL operations, it can only do so if assigned the owner role. If you have more than one TiDB server in your TiDB database, then these TiDB servers will take turns assuming the owner role. The chosen TiDB server will have the owner role for a fixed time, and this is by election. This time is called the term of office. When a TiDB server has the owner role and is in the term of office, then it handles DDL operations. The current owner role information of the database is stored in the PD. Remember, the PD is the brains of the database. And the workers module can check whether the TiDB server in which it is located is currently the owner. When the term of an owner expires, PD will initiate the selection of a new owner. Secondly, in addition to the worker module, there's also a schema load module. This module is used to load the latest schema information after a TiDB server assumes the owner role. This ensures that the new owner role TiDB server has the most up-to-date schema information. Finally, the Start Job module is responsible for receiving DDL requests and assigning IDs to DDL operations. Each DDL operation assigned an ID is called a job. The start job will persist the job to the queue in TiKV. TiDB's transaction implementation uses a multi-version concurrency control, or MVCC, mechanism. When newly written data overwrites the old data is not replaced. It is kept at the same time as the newly written data, and the versions are distinguished by a more recent timestamp. In other words, the version of the data with the most recent timestamp is the one that is used. The garbage collector's task is to clean up old data that is no longer needed. The principles and implementation of MVCC and garbage collection processing will be covered in the TiKV module. One TiDB instance in the TiDB cluster will be elected as the garbage collection leader. The garbage collection leader controls garbage collection for the entire TiKV cluster. Garbage collection is triggered periodically. At each garbage collection point, TiDB Server first calculates a timestamp called a safe point. By default, garbage collection is triggered every 10 minutes. That is, the default garbage collection lifetime is 10 minutes, and the safe point is calculated as the current time minus garbage collection lifetime. Next, let's look at TiDB Server Cache. The TiDB Server Cache is greedy and uses all of the server's available memory by default. First, let's look at where memory is used. When complex SQL queries such as hash joins and queries with many subqueries are used in the execution plan, TiDB Server will use a lot of cache. When these operations cannot be performed entirely by coprocessors, that is, operations pushed down to the TiKV node, the data must be sorted in TiDB's server cache before it can be returned to the user. Update and delete processing can involve a huge amount of data and therefore will consume a lot of cache. Threads are cached in TiDB Server, and if there are many active threads, that will also use a lot of the server cache. The table metadata, information schema, user authentication, authorization data, and statistics are also cached. So what are the parameters that we can use to effectively manage the cache? The first one is TiDB-mem-quota-query. This parameter controls the default cache usage of each query. There are additional parameters that can be used to alter the TiDB server cache. You can find these in the TiDB documentation. Look in the Configure Memory Usage section. Next, OOM-action. If you set OOM-action to cancel, memory usage of a SQL statement that exceeds a certain threshold will immediately interrupt the execution of the SQL statement and return an error to the client. The error message will specify in detail each physical execution that takes up too much memory. In TiDB version 6, PingCap introduced the cached table. This is also called the TiDB Hotspot table cache. The entire table's data is loaded into TiDB server memory. When we query the cache table, we read directly from memory. This improves performance. You're probably asking yourself, how do I cache a table? It's easy. Let's assume you have a table named user. This table is read often and rarely updated. We can empower this table to use cache by issuing an alter table command. The command is alter table users cache semicolon. The TiDB Hotspot table cache. The amount of data in the table is very small. Currently, TiDB has a limit of 64 megabytes per cache table. The alter table cache statement will fail if the table contains more than 64 megabytes of data. It's important to note that a lease is added to the cache table and that the lease duration is determined by the system parameter. The TiDB_table_cache_lease definition defaults to 3 and can range from 1 to 10 seconds. In the case of a graph, the timing starts when the table begins loading from TiKV's cache to the TiDB server. During the lease time, we can read the table in the cache on the TiDB server, but write operations are blocked. In other words, the table cannot be modified while the lease is active. When the lease expires, the data in the cache also expires. At this time, all read operations will retrieve data from the TiKV node, and write operations can be performed. When the data is updated, the lease starts to be retimed, and the write operations continue to be blocked. At this time, the data is reloaded into the TiDB Server cache, and the read operation can retrieve data from the TiDB Server cache. This is a great time to review the hot table cache use constraints. Currently, TiDB has a limit of 64 megabytes per cache table. Here are some typical use cases for TiDB cache tables. Configuration tables for applications. These are typically read every time the application starts. Perfect use of a cache table. A table that stores exchange rates in financial scenarios. This table is not updated in real time and is only updated once a day. Branch bank or branch information forms, which rarely adds new entries. Anything that has a lookup table is also a candidate for this. Direct DDL operations on cache tables are not supported, and the cache needs to be shut down first before you can do DDL operations. For tables that load slowly or are rarely modified, TiDB table cache lease can be extended appropriately to maintain stable read performance. We have covered a lot of material during this module. I feel confident that we have met all of the objectives defined at the beginning. First, we can describe the overall architecture of TiDB Server. We can describe the main functions of TiDB Server. And finally, we can describe TiDB Server modules and cached table features. Thank you for taking the time to view this module. We hope you enjoyed it and learned a lot.